So welcome everyone to the Metrics International Forum. The forum is organized by the Meta Research Innovation Center at Stanford, or short Metrics. The center is directed by John Ioannidis and Steve Goodman, and we are a research group and fellowship program dedicated to finding ways to improve the validity and transparency of scientific research. I'm Mick Siebert, a postdoc here at Metrics, and I will be today's moderator. All of our international forums are recorded and can be accessed on our website. Please keep your questions until the end or write them in the chat during the presentation. Our presenter today is Marek Kwiek. He's the UNESCO Chair in Institutional Research and Higher Education Policy at the University of Poznan, Poland. His research area is quantitative studies of science, with interest in globalization of science, global science elites, and international research collaborations. He spent 3 years at North American universities, including the University of Virginia, UC Berkeley, and McGill University. Currently, he is a visiting researcher at the German Center for Higher Education Research and Science Studies in Berlin. So if you're ready, Marek, we can start.
Okay, thank you very much. Good morning, everyone. It's my great pleasure to be back here. I'm once a year here. This is my third time here. It's going to be a story about leaving science forever. You come, you start publishing, and you no longer publish, not anymore. It's going to be longitudinal, so I will be studying scientists over as much as 23 years. It's going to be cohort-based, so I'll be discussing a number of non-overlapping cohorts, and I'll be discussing generally millions of scientists. They all come from the OECD area. And most importantly, gender differences, how men and women differ in attrition. Okay, just three slides of very brief introduction. What questions which were driving our research? Can we really quantify leaving science? Can we? Yes, the answer is yes, we can. We're interested how attrition or leaving science differs between men and women, women, then across disciplines, STEM disciplines. And does it differ over time if we take different cohorts? Is it different for different cohorts? My answer is yes, it is. So we work at a very individual level. We look at attrition from a global perspective, from a longitudinal perspective, and to the question whether this type of analysis can be done meaningfully without Scopus type datasets or large-scale datasets, the answer is probably it's not possible. So this is a combination of big data, in this case Scopus, which allows us to look longitudinally, look globally, and track scientists over time for, well, as many as 20 years. I'm talking about leaving science, but it's not really the same as exiting research or leaving academic employment, leaving the academy. All those concepts are different, but ceasing publishing, leaving science is what is accessible today through big data. Leaving science in terms of ceasing publishing. What we do in the more general terms, we test new possibilities opened up by global bibliometric datasets in studying global careers, in studying global scientific careers. So we have some traditional narratives about leaving science, and we have new global dataset, and we see what happens. We know those, even in very popular versions, we know these traditional narratives on attrition. For instance, we know from past research that first, women tend to disappear from academia earlier than men. We just know it from many previous studies from the past 30 years. And we also know that women tend to disappear in higher proportions than men. We know it, we discuss it through many theories, say Chile climate theory, or say wiki pipeline theory. All those theories are around us, we just know it. And in our case here, we test these traditional narratives using 2.1 million scientists from 11 non-overlapping cohorts. We track people over time, track people over 2 decades, and see how they disappear from science and relate it somehow to traditional narratives. Well, finally, the last slide of introduction. Why is it all possible? Why can we do global studies and can we do longitudinal studies of academic careers today? There's only one reason, because we have access to digital databases like raw Scopus dataset or like Web of Science dataset, but not so easily. I will explain why Scopus is much more useful for these purposes. So we have access. We have because of those databases, we have comprehensive accounts of individuals. We have all those research outputs by year, citation impact by year, and we can build what we term here individual lifetime histories from the first publication ever to the last publication ever, with all other individual level information available. So what we can do basically with what we are doing here, we explore career histories of hundreds of thousands, and in our case here, millions of individual scientists. It's just possible because of those global data sets, which are expensive, which are not non-accessible, which are difficult to run and expensive to run, but they are around. So what we did in the past few years in Poznan, I discussed, well, we did 3 strands of research recently, and I discussed all of them, or will discuss in a second here at Metrics. Women in science, or young women, we discussed it last year. And the big story for 2 decades is available in quantitative science studies now. Just a few weeks ago, it was made available. And I discussed it last year. 2 years ago, I discussed productivity classes under this big idea, once highly productive, perhaps forever highly productive. Again, all OECD scientists, more than 300,000 scientists and academics changing productivity classes over time. So we saw it, it's available as a preprint, and today is Living Science, quantifying attrition. Again, a preprint is available. And what drives these 3 strands of research for us? First, we turn bibliometric data like Scopus into individual level data. We don't think about publications. We move toward individuals as a unit of analysis. So we have individual scientists, not really their publications, but we have the publication, obviously, but the focus is on individuals. So bibliometric data are turned into data about academic careers. Well, is Living Science a new scholarly theme? Well, it's certainly not. But what is new, perhaps, is examining Living Science longitudinal, like year by year by year by year, and also examining this phenomenon globally, with a focus not on the US, as in 95% of cases, but with a focus on disciplines, mathematicians, astronomers, chemists, etc. This is something I would say which was not examined so far, because traditionally what was explored under this theme, US institutions or US scientists, small-scale studies, case studies, research, mostly, if not almost exclusively, surveys and interviews. So these were more or less cross-sectional studies, a point in time, and the US definitely. But still, in surveys and interviews in the past three decades, we know how quitting science can be explained. We have all those explanations, which I will be discussing in a second, from the surveys and from these interviews. So we know why it happens, why attrition happens. Work-life balance is a huge issue. Parenthood is an issue. Well, low job security, low salaries, and workload concerns, increasing workloads, it's an issue. Also discrimination. We also know from a recent study by Katie Spoon about the US that really for women, chilly climates matter more, traditional chilly climates matter more than work-life balance. So there was a large survey in the US on this issue, and we know it. Still, we know that attrition depends on a combination of push and pull factors. Some factors kick us out of universities or science sector, and other factors pull us into outside of the science sector, like companies, or out of science sectors altogether. So there's a combination of push and pull factors. This research was done with my doctoral student, fantastic Łukasz, who may be with us today, but maybe not, because he's just finishing these days as we speak. These days, next week actually, he's finishing his PhD after 4 years, so he may be not here today. But still, this is a joint product the free products are our joint products. So how this research is different. First, geographical scale. It's not the US. It's we are moving away of the US, of its single country research design. We are interested in disciplines, all mathematicians worldwide, or all astronomers worldwide. Well, not really worldwide, but in 38 OECD countries, and over time. So we move toward disciplines, and we move toward temporal changes, year by year by year by year. And we use survival analysis. Our cohorts are huge. They are not overlapping and really huge. And maybe one more idea. This is a study which is strictly longitudinal. Strictly, we really cohort thousands and in this case millions of scientists over time, exactly the same scientists over time for up to 22 years. We use a wealth of micro level data. Why survival analysis, which is normally used for death or recovery from illness or mechanical failure of cars or whatever? It's useful. We study survival time in science. How many years men or women or mathematicians or whoever survives in science, meaning publishes, because we compute probabilities of occurrence of an event, and this event is stopping publishing. We see what happens when this event happens. Event is not publishing anymore. Scientists at some point stop publishing for good. We are not able to discuss whether scientists leave universities or not, because we don't have this type of data globally, but we can clearly see that they stop publishing for good. And we can define these probabilities through survival analysis. We have frequency analysis for all publishers. We know how they published, so it's relatively reliable story. We somehow revisit theories of women leaving science. Somehow we're not really interested in kind of testing exactly how it works, but it's a good theoretical background. We know, for instance, that there may be hostile work environment in STEM fields. Women don't go there, don't pursue careers there because they are not really welcome. This is Chile climate theory developed over 3 decades. And also there's leaky pipeline theory, perhaps even more important and even more famous, which says that there's a loss of talent, of scientific talent at every stage of academic career pipeline. We just know it. We're told that women, but I will tell you also men, powerfully disappear at every stage of this career pipeline. The data set, very briefly, we have, this is a graph for 2 cohorts, cohort 2000 and cohort 2010, but I will be discussing all 11 cohorts between 2000 and 2010. Cohort 2000 is every scientist in STEM who had first publication ever in year 2000. This is the cohort. And we follow this cohort for up to 22 years. And cohort 2010 is exactly the same. It's just first publication 2010, and we follow the scientists over all years up to 22 years. All in all, our cohorts are 2.1 million scientists. We had to define non-occasional status of the scientists, so they need to have at least 2 research articles to be in our sample. We need a clear country affiliation for everyone. Clearly, is it Poland or is it US? We need clearly defined gender in a binary manner. Is it male or female with some probability threshold? And we also have to have clearly defined discipline, a STEM discipline. We did it through pretty complicated procedures. Just to give an example, how we defined discipline for everyone. We did it through cited references of all publications, lifetime of everyone. So we had 1.4 billion cited references, well, the whole pool of references, and the modal value was found based on these references, which pinned down everyone to a single STEM discipline. We also had a modal value of country affiliation, just one country, not many countries or 2 countries. We had this academic age, which is equivalent to publishing experience of scientists, and many more, which I'll discuss in the next slide. You have list of STEM disciplines. We discussed basically Scopus classification. So we had 16 STEM disciplines. It was easier than anything else, and easier than using, I don't know, 38 national classifications of sciences. It is just one of those proxies which we are using in this this study. So actually STEM disciplines are kind of Scopus STEM disciplines. And what we had for everyone, I wouldn't say what we had to compute. We computed a number of micro level data for everyone. Well, if you look here, you have IDs from 1 to say, well, 2 million, and you have a number of micro level attributes. Just to give an example, this ID 142776 is a male coming from Germany, defined as working in the field of medicine through all his lifetime cited references. He doesn't work really in a globally top institution, top 200 rest, so he's working somewhere else. His first publication, so it's cohort 2000. His first publication was in the year 2000. He stopped publishing in 2016. What we computed about him, what we know, we know that he was relatively highly internationalized as far as medicine is concerned. 1/4 of his publications was written in an international company, about 1/4. We also know that he was publishing in lifetime. He was publishing in pretty good journals, because the Scopus percentile rank average lifetime was 72, which is pretty good if we take all 30 research papers he published in his life. For medicine, he was working in small teams, because the average median team lifetime had the size of 3. So it was he and 2 collaborators. So small teams generally, and relatively well cited, or with relatively high impact. He had twice the impact field weighted citation impact compared with others at the same time in the same discipline of medicine. And we know that his output was 30 publications. And this type of individual level data we had for everyone. We had many more, but for this study we used just these. We did frequency analysis so that we knew how people publish, how often they publish. And what is important for us is that we use a window of 3 years. After 3 years, in year 4, someone disappears from science if he's not publishing. So we know that in this case, if the break is 3 or 4 years, we are talking about 1% or 2% of scientists. So generally, it's more or less correct. We don't expect people publishing every 4th year or more, because it's just 1% of them. So we just know it from frequency analysis. We're coming exactly to attrition. We use Kaplan-Meier's estimates for this cohorts 1 by 1. Here, the first cohort 2000. And we are interested certainly in women compared to men. So we have women on the left and men on the right, and time in years from year 1 to year 19, which is the last year in our study. And basically, Kaplan-Meier estimates multiply probabilities of survival for a given period of time. For instance, if you look at those red squares, in year 10, the probability of women of staying in science or keeping publishing is less than 50%. And for men at the same time, it's 54%. So we can see already the difference year by year in probabilities to stay in science. Men have higher probabilities to stay in science, but it's much more easier to see it graphically. You can see declining horizontal steps. Well, for all disciplines combined, for men and women, we have years of publishing from 0 to 22, and we have proportion staying. And we can see how scientists disappear from science year by year. And we can see on the left, this is cohort 2000, that the probability of staying for men is much higher. It is definitely higher. And this is expected. But what is unexpected is when you look at the most recent cohort 2010, there are basically no gender differences. You can see these declining horizontal steps are just, well, overlapping to an extent. There's no difference, statistically speaking, and we verified there is no difference. And this is all disciplines combined. But when we move on to disciplinary variations, we can see enormous differences. We did all stories and all figures for all possible disciplines for all cohorts. And what we can see is that in disciplines when the share of women is very high, like almost 50%, women have much lower probability of staying, and the difference is enormous. But in those specific disciplines, math-intensive disciplines, I call them Big Four, and I call them Big Four. Last year and 2 years ago had metrics, like mathematics, computing, physics, and astronomy, engineering. There's basically no difference at all. The curves are nearly identical, or they are just overlapping. And the question is, why is it so? We did a number of tests. Obviously, we see the differences are statistically significant. We know it. The question is, why? Why there are no gender differences in survival curves in the Big Four? And I was thinking for a long time why it may be happening, and still have no answer. But one of the answers could be that there is very low representation of women in this Big Four: physics, computing, mathematics, astronomy, engineering. And it may still happen that what Cantor discussed in companies in the 70s is still an issue in universities today, and it's proportional scarcity. If women are below 20%, like 15%, 10%, they may be under high scrutiny, highly visible. Everyone can see them, and it's possible they are pushed. First, they are extremely talented, but they are also pushed to be hardworking because they're clearly visible. So maybe they're highly competitive from the very beginning, or maybe they are pushed to be highly competitive. No matter what, it's one of the answers. Another is perhaps self-selection of men and women into STEM disciplines, which we are aware of, but also into the Big Four, which is a radical version of STEM because it's highly mathematized. So we discussed it, and I came back to the story which I presented at Metrics last year, which is a snapshot of 1 year, 2021, and how women and men are distributed along age groups within disciplines. And when you look at the cases of computing, mathematics, physics, you can see that there's no increasing proportions of young women in these areas. So let's look at computing. In the oldest age groups, the share of women is just 15%. And in the youngest age group, just today, working for 5 years, it's below 20%. And when you look at total downstairs, you see there are more and more women around. If you look at biochemistry and bio, which is biochemistry and molecular biology, half of young scientists who publish today are actually women. So this is probably, this makes a difference. There is no inflow of women into these areas. Consequently, women in these areas need to be enormously competitive and also enormously hardworking because they are just visible. You can see here on the right the trends we did over 30 years, and also years needed to have gender balance, which is about 100 years or 80 years. It's another story, but I just wanted to give you a context. We have observed huge inter-cohort differences. So on top, we have cohort 2000, those who started publishing in 2000. And at the bottom, we have cohort 2010. And you immediately see, well, we use 4 different measures in panels A, B, C, and D. We use Kaplan-Meier curve, which I discussed, but we also use survival regression curves for men and women, which is kind of smoothed Kaplan-Meier curve, hazard rate curve, and finally, kernel density curve, which shows what is the distribution of men and women who actually left over time. And you can see that for the first cohort, the oldest cohort, that gender differences For the second cohort, again, there are no differences. So 10 years passed, new conditions, new environment, and no gender differences at the level of all disciplines combined. Certainly, this is a big story. When we look into smaller scale stories into disciplines, there are differences, like in this bio versus physics and astronomy stories, but I'm not going to get into details. Anyway, in large scale, gender differences are smaller and smaller. So attrition patterns are less gendered over time. We studied 11 cohorts, non-overlapping, one by one, and we were tracing these attrition patterns. And the conclusion is that time really matters. Time in science matters, because environment for doing science is just different for every new cohort. Every cohort experiences attrition differently. So all those differences which we have seen here for the oldest cohort are not really visible here for the youngest cohort. And I would say this is a dramatic difference. So what basically was valid for older cohorts, what we also knew from all those US stories about US scientists 30 years ago, maybe no longer valid, because time matters. And I can show it in big data that as cohorts change, also attrition changes. And still we have big stories and big theories which might be tested. I'm not going really to test it carefully, but it might be an issue. What is working for the old doesn't have to be waiting for the young cohort. And just one area which is not my area, but which is perhaps interesting. You know that behind this big story of 38 OECD countries, there are smaller stories from every OECD country. So big story and smaller stories. And there is a place which I will give you address to in a second in the chat. It's an online interactive dashboard which Łukasz prepared with probabilities by country, but also by discipline, but also by cohort, because we have 11 cohorts, and also by time. So what happens to chemists in the US from cohort 2000, men, after 15 years? What is the chance to survive? And the chance to survive in the US, here you can see on the right, in chemistry is 28% for men. But it doesn't make sense unless you compare it to Portugal, Poland, or Lithuania, where this chance is as high as 50 or 70%. So nationally, you can see that attrition differs enormously. If you look at colors, it's from 0-17, which is 17%, to 70%, actually. You move the map from part of the world to another part of the world, and you see how career prospects are just different by country. But my story is a global story. This is just a kind of data behind this big story. One slide of limitations and three summarizing slides, and we are over. New limitations. First, stopping publishing is here. Leading science is understood as stopping publishing. And we know that people can be doing teaching, doing service, doing administration. It's all true. But in our understanding, it's not doing science anymore. So we know this in science, out of science, concepts are slippery, but still we keep it simple. We have a simplified approach in which if you don't publish, you are not doing science anymore. The answer is why we do it. The answer is we don't have any type of data globally to think otherwise. We have only publishers and non-publishers. We don't have employment data, for instance, not at all globally. We can do everything in the US or in Poland, but not really globally. So just three final slides. We do a lot of national studies, and we do quite a few global studies, and we see the differences. What type of data are available nationally and what are absolutely not available globally? This is biographical information, year of birth, employment, promotions. We don't have it. You can have it through academic analytics in the US. You can have it through Kristin in Norway if you have perfect access to the data, but globally it's not available. So there's a number of methodological issues which need to be made clear. For instance, nationally perfect data from national registry, globally just inferred data or proxies. It makes a big of difference, but I would say the trade-offs are needed if we want to move in some other directions. For instance, move beyond the national analytical container of the US or a single country approach. And final words first. If we want to move beyond single country or countries, a few countries, and examine attrition over time, we need longitudinal global data sets. To me, at the moment, Scopus is one of them. We know that attrition in science means different things for men and different things for women in different disciplines. You remember these figures. It means different things for different cohorts also. So it's men, it's women, it's disciplines, and it's also cohort. Attrition depends on when you entered the academic profession or the science profession. And finally, the very last slide, we can easily see the gender differences in attrition in science are smaller with each successive cohort. This is the good news. The bad news is the news from the big picture, which I have shown you, that the participation of women is very, very small and it's not increasing. So it's somehow smaller gender differences in attrition, again, big gender differences in participation by discipline. And even more so, attrition is very high. 60% of scientists disappear within a decade, 60% globally. There are differences by country, as you can see, but globally, all in all, it's 60%. It's very high, it's on the rise, and it's on the rise. But finally, it's a problem for both men and women. This is maybe one of the major messages. Attrition is not an women issue, it's a men and women issue. The question is why we massively leave science, why we massively leave academia, and the answer is we don't know it from big data analysis. We just can't know it. We can know it from surveys, we can know it from interviews, and this is where qualitative studies are enormously useful. We can see patterns in big data, we can discuss the patterns, but why question is another type of question. This is where surveys come in handy and interviews come in handy. Okay, thank you so much. It's more than enough. I believe it's half an hour, and I'm very much open to any discussion we may have. I'm just stopping sharing the slides, and I'm all for you if you're only interested.